Hello! Today in general physics, we're going to be looking at word problems that involve falling objects. Now, the problem-solving strategies for falling objects are the same as any problem-solving strategy that we would do for any word problem. We're still going to create a table of knowns, and we're still going to use those knowns in order to figure out what algebraic equation is going to help us solve the problem. But the thing about falling object problems is that they don't necessarily give us every single number written out every single time. There are some keywords that are used that are supposed to tell us some of our knowns without whoever wrote the problem having to spell it out for us every time. So, for example, if we know that something is falling, we know that the acceleration of that object is going to be negative 9.8 meters per second squared. Right? So the person who's writing the problem doesn't need to say that to us every time. As long as they use the word falling, we can make this assumption in our knowns table. Something being dropped tells us that we've got an initial velocity of 0 meters per second. And when we have something reaching its maximum height, we know that the final velocity of that object is going to be 0 meters per second. Because when something is thrown up into the air, at the very moment it's at the peak of its motion, it briefly stops and then falls back in the other direction. So let's do some 4 practice problems to show this. A rock is dropped off a bridge and into a river. The rock falls a total of 180 meters before hitting the water. How long was the rock in the air? So as we write out this knowns table, we see that we are going to fall a total of 180 meters. And really, that's the only number that's given to us in this problem statement. We have to use our keywords to find the rest of the knowns. So because this rock is dropped, we know that it has an initial velocity of 0 meters per second. And then this thing is falling, so we know that its acceleration is going to be negative 9.8 meters per second squared. And ultimately, we want to know what is the time that the rock is in the air. Now, one thing to note, by saying that the acceleration is negative 9.8 meters per second squared, we're using conventional coordinates, which means that any positive value is up and any negative value is down. And so since we are falling down, that also means that our delta x gets a negative. So it's really negative 180 meters. Don't let those positives and negatives freak you out. Again, they just are supposed to mean direction. Now looking at this, we know delta x, vi, a, and delta t, those things are all combined in delta x equals vi delta t plus 1/2 a delta t squared. So let's plug in everything we know. Negative 180 meters is equal to, now this initial velocity was 0, so that whole thing goes away, plus 1/2 times negative 9.8 meters per second squared times delta t squared. And from here, we just need to use algebra in order to solve for delta t. And when we use algebra, we find that the delta t ends up being 6.06 seconds. Let's do problem number 2. Oh, actually, problem number 2 is an extension of problem number 1. Using the rock in question 1, how fast will the rock be going right before it hits the water? So when we write out the knowns for this problem, we already have a bunch of knowns. We know that our delta x is going to be negative 180 meters. We know that the initial velocity of this rock is 0 meters per second. We know that the acceleration is going to be negative 9.8 meters per second squared. And now we know that the time that the rock is in the air is 6.06 seconds. And ultimately, we want to find how fast that rock is going when it hits the water. So we want to know what our final velocity is. Now, looking at this, especially if we didn't know the answer to part A, I would probably use VF squared equals VI squared plus 2A delta x in order to solve. So our final velocity squared equals, well, the initial velocity was 0, so that goes away, times 2 times negative 9.8 meters per second squared times negative 180 meters. And so when you do the math, you end up getting a final velocity of 59.4 meters per second. Now, we have to ask ourselves, is this final velocity up or is it down? Because right now we're saying that this rock is ending with a velocity of 59.4 meters per second up because it's positive 59.4 meters per second. But really, we know that this rock would be falling down, so we're going to add a negative sign out there to show that this rock is in fact going down. This makes sense because we know that when we square something, a negative value squared is the same thing as a positive value squared. So when we take the square root, we can choose either the positive or the negative answer. And in this case, we're just going to choose the negative one to show that this thing is going down, moving with a velocity that is down. Let's go to number 3. Sue throws a ball up at 5 meters per second. If she catches the ball at the same height at which she threw it, how long will the ball be in the air? So we got a bunch of knowns here. We know that Sue is going to throw this ball at 5 meters per second. Now she's catching the ball at the same height at which she threw it, so that means that our total displacement ends up being 0 meters. And this ball is being thrown into the air, so that tells us that our acceleration is going to be negative 9.8 meters per second squared. We ultimately want to know how long will it be in the air, so we're going to be looking for that delta t. Now these are the same 4 knowns that we had up in problem 1, so let's do what we did in problem 1 and use delta x equals vi delta t plus 1/2 a delta t squared. So we end up getting that 0 meters is equal to 5 meters per second times delta t plus 1/2 times negative 9.8 meters per second squared delta t squared. Now, for those of you who are big math fans, you might be saying to yourself, ooh, this looks like a quadratic equation. And you could certainly set this up like a quadratic and solve it. However, let's use this 0 to our advantage, because if we divide both sides by delta t, 0 divided by delta t, well, that's still just 0. But then when we do 5 delta t divided by delta t, this delta t goes away. And then when we do 1/2 times negative 9.8 times delta t squared divided by delta t, that causes that squared to go away. So what we end up with is 0 equals 5 meters per second plus 1/2 times negative 9.8, that's negative 4.9 meters per second squared times delta t. And now it's just algebra, which is really great. So we end up with 4.9 delta t equals 5, and therefore your delta t is going to end up being 0.98 seconds. Finally, the last problem, we're going to use the information in problem 3, how high will the ball go? So all of our knowns are going to be the same as they were in problem 3. Our VI is 5 meters per second. Delta x is 0 meters. Acceleration is negative 9.8 meters per second squared. And our time is 0.98 seconds in case we want to use that. So what we could do is we could use Vf squared equals Vi squared plus 2a delta x to help solve this. Because if we want to know how high the ball goes, that's really talking about the peak. And we know that at the maximum height, also known as the peak, we know that that final velocity is going to be 0 meters per second. So we actually could add that to our knowns table. Vf is equal to 0 meters per second. So we end up getting that 0 equals 5 meters per second squared plus 2 times negative 9.8 meters per second squared times delta x. So then we can do the algebra. I think this ends up, if we move this 2 times negative 9.8 times delta x over to the other side, we end up getting 19.6 delta x is equal to 25. So we divide both sides by 19.6. And you end up getting that the maximum height is going to be 1.27 meters. And you know what? There's actually another way that we could have solved this problem. This is really just problem solving method number 1. The cool thing about kinematics is that as long as you have lots of information, you can solve these problems using any equation that you want. So just for fun, let's try to solve this problem a different way using a different equation. Now this ball is being shot, right? And then it's coming back down and it's landing. So it's being shot and it's coming back down. Now the time it takes for this thing to go up to its peak is going to be 1/2 of the total time that this ball is in the air, right? Because it's shot and landing from the same place, so as much time as it takes to go up, it must take the same amount of time to come back down. So we can use that to our advantage here, seeing as the fact that we already know that the total time is 0.98 seconds. So using that, we could use delta x equals vi delta t plus 1/2 a delta t squared and solve this problem using an entirely different equation. So our delta x is going to equal 5 meters per second. And then for my delta t, I'm not going to put in 0.98. I'm going to put in 0.98 seconds divided by 2 because the time to the peak is half of the total time. And then plus 1/2 times negative 9.8 meters per second squared times 0.98 seconds over 2 squared. And this method of solving is kind of nice because we don't have to do any, moving things back and forth to the other side of the equal sign. We can just plug all of this into our calculator. And when you do, you get that delta x is 1.27 meters. The same answer that we got when we solved this problem using an entirely different equation. And that is so cool. That means that there are multiple ways to solve problems, which means that you can really solve these problems in whatever way you feel comfortable, and as long as you have enough information, you should be able to get the answer correct. So good luck solving free fall problems.